All right, we've been talking about exponential, logarithmic, and logistic models. Let's look at some examples. And I'm going to share my screen. We've got a PowerPoint here to talk about these models. So in the first example, we are given some data here, and it's the atmospheric pressure, which is the dependent variable, and that's in millibars. And it depends on the altitude x in meters. So here's our data. It says to make a scatter plot, and it asks what type of function might model the data. So if you look at the data, you can see here a rapid decline. This is exponential decline. And if you reflect this across the y-axis, it would be kind of like a increasing function, but it's declining, and it's still exponential. It's declining very rapidly. Here, if you enter the data in your graphing calculator and do a calculation, you recognize it's exponential, so you're going to select this option 0 here, and then it's going to give you these values A and B, and you're going to note that it's A times B to the power of X. That's what this caret here represents. X is in the exponent, and the A value is given as 1105 approximately, and B is approximately 1 if you round it. So this is the best fit for this data. In another example, your data, here's your data. And this time we are doing a scatter plot where it's interest rates for certificates of deposit, and you've got time is the independent variable, and the yield, the percentage, is your dependent variable. This particular data looks like this if you do a scatter plot, and that is obviously a more logarithmic. There is an increase, but the increase is leveling off slightly. And it's not really level, it still is going up. So there's no bound on this increase, but it's just not as rapid as an exponential increase. So you can see it's bending downward instead of upward like an exponential graph. So this is obviously logarithmic, and because it's logarithmic, it's going to follow this model here, y equals a plus b times the natural log of x. And if you choose 9 for the natural log regression, you're going to get values A equal 0.143 approximately, and B equal 0.334 approximately. All right, so these are the type of problems you're going to be doing in your homework. There are only 12 homework problems because you are going to be entering in a lot of data. But let's talk about the logistic model. If you want to use Desmos, you may. I suggest that you practice on your graphing calculator, so when you get to the test, you'll feel much more comfortable with it. But I'm going to use Desmos as a demonstration for this video. And here is the formula for a logistic model where you have rapid growth and then a very obvious leveling off. And then there's kind of a cap to how high the function can go. And that is the horizontal asymptote y equals c. So this is what the data for a logistic model looks like, and here's the data that I entered into Desmos. So I'm going to go ahead and share my screen so we can look at the Desmos, or share a different screen, I should say. Here, I already did a best fit, so let me take that off and I'll show you how to do a best fit. Here's the data from the example, and it's obviously logistic. It starts out increasing rapidly, and then it switches to more of a leveling off. So that is a classic logistic model. And the way we would try to fit this to a curve is we're going to enter in, instead of y equals some function of x, we're going to say y1 is approximately equal to some function of x. This is how Desmos does their regression. So you're going to take Y, and you can't see this on the screen, but what I'm doing to get a subscript is I'm taking shift hyphen. And that gives me the subscript. I'm going to enter in 1. And then I'm going to enter in the shift, and it's in the upper left-hand corner on my keyboard. It's approximation symbol. It's a squiggly line. And now I'm going to use I can recognize this data as logistics, so I'm going to use the logistic model, which is C divided by 1 plus A E. Now I'm going to raise it to the power of negative bx. And the way I do that is I shift caret, that takes it up into the exponent minus bx. Now, you might say, well, where's the regression line, the best fit line for this data? I can't see it. Well, I made a mistake. And this is a common mistake, and that's why I wanted to point it out. The x has to also have a subscript of 1. So I'm going to, again, you can't see this, but I'm shifting and I'm hitting the hyphen after I shift, and that gives me the subscript. Now, when I enter in 1, you'll see my best fit line. It's not perfect. You can see that these data sets do not lie exactly on the line, but they're very close. And these, you can see our R-squared value is almost 1, so it's almost perfect. And we have C is 661.8, A is 74.46, and B is 0.55. And this is the model right here, the logistic model. Now, I want to show you that if I type in, I'm going to press enter, and then I'm going to type in Y equals C. C is the constant in the numerator, which is 661, and you can see it draws the horizontal line, which is an asymptote. And if I zoom out, you can see that more clearly. And I'm going to go ahead and also draw in Y equals 0. That is the other asymptote. So the data is bound by these two horizontal asymptotes, and we have that sort of stretched out S curve there, if you will, that looks very logistic, like a logistic set of data, which is what it is. All right, so I hope this helps you go through the homework. And if you have any questions, always please don't hesitate to email me with your questions about this if you're struggling with these problems in your homework.